Okay, in this video, we're going to go over the notes for 5.3, and in 5.3, we're going to use angle bisectors of triangles. So as usual, we start out with some vocabulary. So an angle bisector is a ray, so we should write the word ray right here. So it's it's a ray that divides an angle into two congruent adjacent, that says adjacent, well, let me cut that and we'll print it, adjacent angles. Alright, so if you want to sketch that, if you have an angle bisector, so if this is my angle, if I have a ray that's coming through it, so here's a ray with an arrowhead, it's going to divide that angle into two equal angles. Alright, next thing, point of congruency of angle bisectors. So now we're in a triangle, and if you're in a triangle, if you have angle bisectors for each of these angles, what's going to happen is they will all connect right here in the center of the triangle. That is the point of concurrency of the angle bisectors. So a point of a triangle where all of these angle bisectors intersect. Okay, that's the point of concurrency. So this point, point is called the in-center. So write that down also in your notes. This point is the in-center. And where is it? It's in the center of the triangle. So it's easy to remember. Okay, I'm going to get out of the red. Okay, the distance from a point to a line. Okay, so the length of the perpendicular segment from the point to the line, as we talk about in on page 312. So whenever we talk about the distance from a point to a line, it'll always be the length of the perpendicular segment from the point to the line. All right, let's go over the theorems that come in this section next. Right? Our first theorem is the angle bisector theorem. You can read about this on page 312 in your textbook. So if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. All right, so let's see how that works. So if ray AD bisects angle BAC, so that's this angle right here, and DB is perpendicular to AB, and DC is perpendicular to AC. So this has to occur, this has to occur, and this has to occur. So if all those three things happen, then we can say that DB, so right here, that segment, equals DC. Okay, you cannot say that unless these other three pieces that I've underlined occur. All right. So now we're going to go to the converse of that, which is just reading it backwards. So let's do that on the next page. All right, here's the converse of it. So if a point is in the interior of the angle, so here point D is what they're speaking about, it's inside angle BAC. So if it's in the interior of an angle and is equidistant from the sides of the angle, okay, so you already have those equidistant hash marks, then it lies on the bisector of the angle. So let's see what has to happen. So the point has to be in the interior of an angle, and it has to be equidistant from the two sides of the angle. So you have two things happening, really three things, if you think that it has to be equidistant from B and equidistant from C. If those things happen, then I know that this point D lies on the bisector of angle BAC. So go back and make sure that makes sense to you. Then what they do is now they take a triangle, because a triangle is made up of three angles. And they're saying that the angle bisectors that we just talked about of a triangle, if you bisect each of the three angles, so I bisected angle A, angle B, and angle C. If I do that, then it says the angle bisectors of a triangle, those bisectors will intersect at a point that is equidistant from the sides of the triangle. Okay? And that's going to happen. So if AP, BP, so look at these as you go, BP, and CP, okay, they are angle bisectors of each of those angles, then what happens is PD, the blue line, equals PE, another blue line, equals PF. They're all going to be the same. Now notice, those segments that we just identified, those three segments are going to be perpendicular to the sides of the triangle. So notice that as well. All right? So, and what is this point of concurrency called? That point is called the in-center. So P equals the in-center. All right, that's the theory behind this section. Now let's talk about the examples on the next page. Looking at example 1, it says we're going to use the angle bisector theorems to find the measure of angle GFJ. So GFJ. So that is this angle right here. So let's see what's going on. I see that I have ray JF. I see that ray JF may divide the angle GFH in half if these segments are equal and if when you draw those lines you have perpendiculars. So if that is the case, then that means that JF must be an angle bisector. And if it is an angle bisector, then angle GFH is going to equal, angle GFJ is going to equal the same value as does angle JFH. So therefore, GFJ is 42 degrees. Okay, now be careful. What if they asked you instead for angle GFH? How do you get that? That's the whole angle. So you would say that it was 42 plus 42, which would equal 84 degrees. So make sure that we're always answering the question. In this case, they wanted the other half of the angle, and so you use the same measure as the measure JFH because that angle has been bisected by ray FJ. Okay? So think about that. Make sure you understand that. Okay, now here's a real world problem. So you have a soccer goalie positioned in front of the net. He is positioned on that line, that yellow line that you see. So let's read the problem. A soccer goalie's position relative to the ball and goalposts forms congruent angles as shown. Okay, so here are the two angles that are shown congruent. Now, notice something. If those angles are congruent, then this ray from B to the goalie must be acting as an angle bisector. So now they're asking us, will the goalie have to move farther to block a shot toward the right goalpost or the left goalpost? So what they are really asking you is is the goalie equidistant from each post? And he is, provided that this angle bisector is true. You know it's true because the angles are marked equal. Therefore, if he's standing on the angle bisector, then he is always equidistant from both goalposts. So you say yes, he is going to be equidistant. There is no need for him to move further one way or the other. So will he have to move? And the answer is no. He's not going to have to move because he is currently on the angle bisector, and therefore he will always be equidistant. No matter where he stands on that, he's going to be equidistant from L and from R. All right, we have another example. We'll do that on the next page. All right, in this problem, I see that I don't have an angle bisector drawn in. However, they want to know for what value of x does P lie on the angle bisector. So if P is on the angle bisector, remember what happens, x, or the segment PB, so PB will be equal to PC. So if that's my equality to make point P be on an angle bisector, then I'm going to set the length of PB, which is x plus 3, equal to the length of PC, which is 2x minus 1. So now we have a two-step problem. Subtract x, subtract x. I'm going to rewrite it since I have nice space here. That gives me this new equality. Add 1, so I have a result of 4 equaling x. That was a two-step problem. Now, does that answer our question? And it does. They're asking me for the value of x that makes those two segments equal, and that value is 4. Now, what if we wanted to check our work to make sure that plugging a 4 in does make those two segments equal? That would be a good idea. If we put a 4 in for x for the length of PB, we would get 4 plus 3, which is 7. If we put a 4 in for the length of PC, we would get 8 minus 1, which is also 7. So I know that my work checks out. Okay, let's go to the next page and we'll go through some of the extra practice problems. Okay, this first extra practice is kind of tricky because I'm not told that I have an angle bisector going on here. So let's figure this out. I can say by a congruency that the two triangles formed by the ray AD are congruent due to HL. Okay, so if I know that triangle BDA is congruent to triangle CDA by HL, because I see I have a right angle, I see I have the hypotenuse in common, and I see I have a leg that's equal. So therefore by HL, I know those two triangles are congruent. Once I know that, the next thing I know is that angle BDA equals angle ADA, so we'll get rid of some of my markings here. So this angle has to equal this angle by virtue of corresponding parts. Okay, if those angles are equal, then that means ray AD is a bisector, and if that is the case, then I now know that angle BAD is also 54. So right in here, this angle is also 54. Okay, so once I've established the congruency, I then can also establish the angle 54 degrees for BAD. Okay, let's look at the next one. Our next problem, it says, 3 spotlights form 2 congruent angles. So the angles are marked up here. See those? Here and here? Let me erase those so you can see it. Okay, is the actor closer to the spotlight's area on the right or on the left? So, if this line, so let me just make this a little smaller. Okay, so if this line or ray right here is acting as an angle bisector, then as I continue down, what I now know is if this is at a right angle, this piece is going to equal this piece, right? Because of the fact that that's an angle bisector. So the gentleman is standing exactly equidistant from each of the spotlights. So it says, is the actor closer to the spotlight's area on the right or on the left? And the answer is he is equidistant, okay, from both spotlights. So he's not closer to either of them. All right? And we have one more practice problem, and then we're done with the notes for this section. So let's do that on the next page. Okay, our last example is very straightforward. We know that if the distance from P to B, so that's the perpendicular distance, if those distances are to be the same, then what must be happening is that ray PB must be an angle bisector for angle BAC. So for what value of x does P lie on the bisector of angle A? It lies on the bisector of angle A if, so get your expression, PB, or get your, I guess, equality, PB equals PC. So what do we have for PB? PB is x plus 8. That has to equal PC, which is 3x minus 6. All right, two-step problem. Subtract x, rewrite your equation. I have 8 equals 2x minus 6. This is a two-step problem. Here comes the second step. I guess it's really a three-step problem. Add 6, that gives me 14 equals 2x. Divide by 2, and that leads me to x equaling 7. Now, they only ask us for x, but let's verify our answer by plugging x into the two segments I've identified. So if you're trying to find BP, 7 plus 8 is 15, using x is 7 in the expression. And for the next expression, for PC, 3x minus 6 is the expression. Plug in 7, you get 21 minus 6. You also get a 15, so that verifies that my work right here, or my work here that led to this, is correct. So that ends the notes for this section. I will go back over this. We've covered a lot of ground in just a few minutes. Make sure you understand this before you go and do the practice problems for homework.